In this video, I'm going to show you how you can make a bar chart and how you can make a histogram using MATLAB. And we'll just start off with something very simple. Let's say we wanted to make a bar chart of like employees' salaries, and maybe we have employees like 1, 2, and 3. So maybe 1 corresponds to some person, 2 corresponds to a different person, 3 a different person yet, and we'll say that that is vector x. All right. So there's vector x. Maybe maybe y is the salary in thousands of dollars. So maybe person 1, there has to be a 1-to-1 correspondence here. So maybe person 1 makes 65K, person 2 makes maybe 80K, and then person 3 makes 43K, something like that. All right, and maybe we want to just draw a simple bar chart with three bars there. So we can just execute the command bar, and we'll just give it x, comma, y, and let's see what pops out. All right, let me dock this, and there we go. There's our bar chart. Now, just like before, as we saw in previous videos, we can click on this button here to show plot tools, and once you do that, you can manually adjust things. Like, for example, if I wanted to change the color, I can do that. So I can click on the bars and I can change the color to, let's say, I can change it to, let's say, green, pink. There we go. And I can also like change the width. Maybe those bars are crazy wide, right? So I can change the bar width here to like 0.4. So that looks maybe a little bit better. So maybe I'm happy with that. And of course, I'd want to give these axes labels, and we know how to do that already. And you know, then I can save it as I've done in the past, just like it's a figure, right? Because it is a figure. It's just that we're using the bar function instead of a plotting function. All right, so I'm going to clear that, CLC clear, and I'm going to just X out of this. I'm not going to save it. And I'm going to show you how you can make a histogram. A histogram is like when you count things and you put them in like bins, like equally spaced bins. It looks like a bar chart, all right, but it's a little bit different. It's like a count of how many things occur, and you can make a histogram. You can apply it in like statistics, so you could definitely use this in statistics. What we're going to do in this example is we are going to investigate MATLAB's rand_n function. This stands for random normal. A normal distribution of random variables is like the bell-shaped curve. All right, so apparently, like if I ask MATLAB for a random number using this function, apparently it gives me a random number between like negative with a standard deviation of 1, I think. And that might not mean anything to you if you don't know statistics, but this is like a bell-shaped curve that's centered at 0, that roughly goes to 1 in each direction, right? And what we're going to do is we're going to generate like a bunch of numbers, like 1,000,000 numbers. So let's do that. Let's say data equals rand_n, and we're going to ask for 1,000,000 numbers like this. Okay, you don't have to understand this command because the focus is on generating the plot, not the data. But anyway, I have 1,000,000 data numbers. Like if I looked at the first one, all right, there's the first one. If I looked at the last one, right, there's the last one. And the question is, do these numbers actually make a normal distribution, a bell-shaped curve? So what we're going to do is use the histogram function to plot the histogram. So I'm just going to call histogram, and I'm going to give it the data. Now this is the bare bones histogram. Let's see what this gives us. And I'm going to dock this so you can see. And there we have it, right? So you can see, yeah, this does exactly what MATLAB claims it does, that this rand_n function is giving us this bell-shaped curve centered at 0 with roughly a standard deviation of 1. And so what this is doing actually though, it's counting. Let me see if I can zoom in on this thing. Yeah. See, each bin has a width, and it's counting like how many times a number falls in each width. And so if a number falls in the width of each bin, then it increments that number. And so after a million times, after a million numbers, let's see. After a million numbers, like this bin here that's centered at -1, we have about roughly 7,000 counts there, right, after a million. So 7,000 out of a million fell in the bin centered at -1. So you could see how this would be like a statistical thing that you'd want. You could get a probability of falling at -1 from this thing here. All right, but we can be a little bit fancier, and I'm going to type help histogram to bring up histograms input arguments. So histogram x is exactly what we did. We gave it one input argument. It plotted a histogram of x. It uses an automatic binning algorithm that returns bins with a uniform width. So you can see each bin has a uniform width there, chosen to cover the range of the elements in x and reveal the underlying shape of the distribution. That's really cool, actually, that it does all of that automatically. That's actually very useful, that you don't have to specify these bins separately. But you could, if you wanted, like you can give it a second input argument m, where m, if it's a scalar, uses m bins. All right, well, let's try that. So I'll say histogram data, and I'm going to give it just 10 bins and see what that looks like. So let's do that. All right, so this is what I get. And you can see, like, that's not great, right? That's actually a lot worse than MATLAB's automatic binning algorithm. But I can ask for 100 bins. Let me do that. There are 100 bins, so that looks better. You can start to see the underlying distribution there is bell-shaped, right? And I can ask for 1,000 bins. I can ask for, whoa, that's a lot of bins. But you get the idea. Now I'm going to go back to help histogram, and I'm going to look at the documentation again. And we can also give the second input argument a vector which specifies the edges of the bins. So if I wanted like some custom bins there, I could do that as well. So this function is very flexible. So let me demonstrate that to you. Let's say I'll say edges equals. I'll give it a vector. Like maybe I want one bin with the edge of 1,000. And then, oh no, 1,000 is no good. How about keep in mind this range here. So let's say -4, and maybe I wanted, for some reason, maybe another bin at like -3, but then I only wanted a bin at 0, like I wanted to skip for some reason, and then maybe 1, 2, 3, and then the last bin maybe at for some reason like 6. Okay, there's my edges vector. Now I'm going to call histogram with my data, and then I'm going to give it that edges vector, and you'll see that the bins are exactly how I specified them. That here's a bin at -4. You can see it a little bit. So not many data points fell in that bin, right? And then here's the bin with its left edge at -3. Here's the bin with its left edge at 0. 1, 2, 3. 3 goes all this way, you can see it there, and then 6, and it doesn't look like anything fell in the 6 bin. So you can use edges, the second input argument, to help you get like a custom, histogram. But I don't know that you need to do that really. Usually, I think its automatic binning algorithm looks pretty good, right? If you just give it the data, it will bin it for you. That's kind of cool. So you'll probably just do that most of the time, but you might also want to just give it the number of bins and let it, smartly decide where the edges are at, like this. So this is 100 bins. 100 bins looks pretty good. Now, one last thing about this histogram is that you can actually get the height of each bin, like programmatically, instead of just like reading it off. And you can say like h equals histogram data 100. So you can actually capture the output of this thing. and we'll take a look at that. Let's look at H. H is actually a histogram with these properties. So you can see the values right there. So we asked for 100 bins, and so we have 100 values now, which is the height of each bin. And I think the way that you would get that is say H dot, is it H dot values? Yes, yes. So if we said H, we'll bring up H again. H is a histogram. They call this an object. So the histogram function returns an object, and it has these properties. And the way you access these properties is with the dot. So you could type H dot values, or H dot num bins would return 100. H dot bin edges would give you the bin edges. But usually you want the height of the bins, right? So you could say H dot values, right? And so this returns the height of each bin. So for example, the last bin way over here on the right side, only 3 out of 1 million fell in that last bin. And same thing over here, like you can scroll up. In the first bin way over here, only 1 point or 1 data point in a million fell in that bin over here. But if we look at like the midway point, like 50 might be, so here's the 50th bin, right? The 50th bin, 37,335 points out of a million fell in that center bin. So you can see that that's correct, right? So you can get all these values, right? And you can turn them actually into a probability. So let me show you that. If H dot values gives you the height of those bins, you can say probability equals H dot values divided by, then we have 1 million. Length of data is 1 million. So now if we divided by 1 million, now we have the probability of falling in those bins. So for example, the probability of falling way over here is next to 0. Let's actually see what it is. Probability of 1. It's 1 e to the -6. So 1 in 1 million, right? That's what we said. Let's see the probability of falling roughly in the middle. The probability of falling in the middle bin is looks like 3.73%, right? And that's because we have so many bins, right? You might have thought that it was higher than 3.73%, but again, we have so many bins that the probability is still low that it falls in any bin, right? But of course that bin's going to be higher than most bins. Like if we look at the probability of falling in the 70th bin, then that's just, that's not even 1%. Alright, so hopefully you get a good idea there on how that you can use the histogram function. Hopefully you can apply that in your statistics class. Thank you.